Hello students, welcome to this new video which is related to unit number 2, Introduction to Thermal Engineering. In this we are going to study the basics associated with heat transfer. Heat transfer is a form of energy. If you try to see this particular slide, it will show you that which passes from a higher body. This already we are experiencing in our day-to-day life, that there is a transfer of heat from a temperature from a body which is at higher temperature to a body which is at lower temperature. As far as the transfer of this thermal energy across a well-defined boundary around a thermodynamic system is nothing but a heat, you can say. The SI unit of this particular term method is nothing but joule. Uh, the overall the flow of heat is all pervasive. The overall driving force is nothing but the temperature gradient or temperature difference as far as the transfer of this particular phenomenon, heat from one location to another location, is considered one. Now when the driving force becomes negligible, then both the systems will be coming at a particular stage which is known as the thermal equilibrium. That means the temperature of both the systems will be similar, will be the similar one. It cannot be directly measured by instrument as temperature is by thermometer. So that is the basic, you can say, difference between the temperature and a heat. Now here initially this particular figure is showing you that whatever there are two flasks. This is one which is by red color, and in which red liquid is available one, and in the another one the another liquid which is at 0 degrees Celsius. This is at 3 degrees Celsius. But after some certain period of time, you can have the thermal equilibrium, that is the temperature of both the liquids is similar one. So that is the thermal equilibrium which is achieved in this particular case. That is the average kinetic energy and the temperature at which the sample of water are equal. We will not go into the details of this one, but just have a quick look at some of the things. Now here in these cases, as far as heat transfer is considered, the exchange of kinetic energy of particles, as far as these two systems are considered, were along their boundaries, are at different temperatures from each other as well as from their surroundings. This already we have seen, from higher temperature to lower temperature there is transfer of heat. But as far as heat transfer, the changes in the internal energy of both the systems involved, which is according to the first law of thermodynamics. As far as second law of thermodynamics defines the concept of thermodynamic entropy, or you can say, which is the measure of heat transfer, you can say. We will see that in our you can say that already we have studied in our second law of thermodynamics. The thermal equilibrium is reached when all involved bodies, that already I have talked about this one, that whenever the thermal equilibrium is reached, when all the bodies which are in contact with each other are having the same kind of temperature. The thermal expansion is the tendency of the matter to change in volume in response to a change in temperature. That is not the very much important term that now which we are going to learn in heat transfer. Now, which are the modes of heat transfer? This is the very basic question which they may you may face in a final examinations, that and define the basic modes of heat transfer, or enlist the basic modes of heat transfer, and how it can be just transferring the heat from one location to another location, in which through which medium, or which are the responsible principles for that. So just try to remember, it can travel through a medium and also through vacuum, that we are knowing. And these are the basic three modes: conduction, convection, and radiation. Now we are going to see all these things in short as far as your syllabus is considered one. But for the time being, remember that these are the three basic modes of heat transfer: conduction, convection, and radiation. Now in case of conduction, a very simple example which is available in next slide, that we will see the transfer of this thermal energy between the neighboring molecules in a substance due to the temperature gradient. That means here, if a rod is available one like this one, and if we are going to heat that particular rod at this particular end, then after some certain amount, a certain period, you will feel that the rod is having this what you can say, the higher increase in temperature at this end also. So here in this case, due to the movement of the molecules from this location to this location and their to and fro motions, whatever the temperature which will be increased from this end to this end due to the conduction, it always it always takes place from a region of higher temperature. So this is the region of higher temperature, and which will be responsible for increasing temperature at the other end to the region of lower temperature, and acts to equalize temperature difference. If at all we are stopping the heating at this particular location, they will be equalizing, or there may be thermal equilibrium. Now such a kind of things already have explained you in solids. The same kind of thing is applicable if a water is available one inside a container, and if you are going to heat it here at this particular location, then the temperature here of the whatever the molecules which are available here, that will go up. Then there is a continuous movement of the molecules of the water which will be inside this container, and there is increase in temperature. So it is available in solids, liquids, as well as in gases. If we place a gas inside this one, then it is applicable to that one also. uh, this is due to the, already have told you, there is continuous motion of the molecules, and due to that vibrational energy between the molecules, it is just responsible for increase in temperature. In gases and liquids, it is due to the collisions of molecules. That is very very important one, during their random motion. That is the transfer of heat due to conduction. Fourier has put forth one particular law related to the heat conduction. It states that the time rate of heat transfer. It states that time rate of heat transfer through the material, that may be solid, liquid, generally uh, that is associated with, he has proposed associated with the slabs, or with any kind of along a particular wall, you can say, material is proportional to the negative temperature gradient. That is, the minus sign is used in that particular mathematical relation to the area at the right angles to that particular gradient through which the heat is flowing. It can be shown like this way, that if this is a wall, and the temperature at one side of the wall is T1, another side of the wall is T2. A is the area through which that particular temperature is available one along with this particular area, so that we can calculate this, what is the heat flow. This is the L, is the length of that particular wall, width of that particular wall, K is the thermal conductivity. So if we consider the case of heat transfer through the wall by the process of conduction, then the rate of heat transfer according to the this Fourier's law is this delta Q is minus K, that is minus this thermal conductivity dt by dx, that is the temperature gradient along the direction of x, and A is the area. So it is directly proportional to the negative gradient, and at the right angles, the area at the right angles. So A and this K is the proportionality constant, which is nothing but the thermal conductivity of the material. So this negative sign is indicating that heat is always flowing from hot to cold areas. So this is very very important one. You will be getting certain examples, numericals on this particular topic. So try to remember, delta Q is the rate of heat transfer, minus that K is the thermal conductivity, A is the area normal to that particular flow of heat, and dt by dx is the temperature gradient. Negative sign is due to the temperature gradient from hot to cold area. Now, in this case, there is another term, thermal resistance, which is nothing but the measure of material's ability to resist the transfer of heat from one location to the another location. The thermal resistance to heat transfer is offered by the wall Rw is equal to B by K, where B is the thickness of the wall, K are nothing but the thermal conductivity, and A is the surface area. This is useful in solving the numericals. Right now, I'm not going to touch through this particular topic in proper manner in details. Another mode of transfer, that is nothing but the convection. Here in this case, movement of the molecules is within the fluids. Convection, that is the movement of molecules within the fluids. In reality, this is the combination of diffusion and bulk motion of molecules. Because it occurs at macroscopic levels, and therefore it is confined to gases and liquids. Generally, it is confined to gases and liquids, and whatever the Fourier's this conduction, as far as whatever we have talked about this one, this is associated with the you can have such a kind of things. See, it can take place in all forms of matter, that is uh, solids, liquids, but does not require any bulk motion of matter. So therefore it's in solids it is due to the transfer of vibrational energy, and in gases it is due to the collisions, and therefore that is nothing but what here in this case, in case of gases and liquids, the motion of this particular molecules is in between within the fluid, that may be gas or liquid. These molecules of fluids are further apart and have negligible cohesive force. Now, this convection currents, that is the motion from one location to another location, is much faster in gases as compared to the liquids because of extremely low cohesive forces which are available one in gases existing between the molecules of the gases. We can have the convection in these two, you can say, ways: natural convection and forced convection. In case of natural convection, actually, mm, here there is no another separate medium which is available. When whatever is taking place, that is at an atmospheric you can say conditions, but here some external forces will be used. One, that maybe air will be blown, or maybe if suppose a very good example of forced convection is if suppose any kind of medium which is used one for just removing the material heat from the hot air surface, or to cool the particular surface, it is the forced convection. Now in these case, actually, uh, I'm just giving you this particular example here. If at all we are going to boil the water in this particular container with this particular holder of that particular container, then whatever the transfer of heat from this one to this, which is coming here, inside this one, whatever is going on, that is nothing but the convection. But from this particular surface of the container to this holder, that is nothing but the transfer of heat through conduction. And whatever is going on inside this particular liquid, that is due to the whatever the internal forces that already I have told you. As far as in these case you can see here, this already has been considered here, that is due to the bulk motion of matter, that is nothing but here it is liquid. So that is the convection. So these are certain examples in which we can have the discussion of conduction and convection. The third, the law which governs this particular convection phenomenon is nothing but the Newton's law of cooling. The natural convection occurs. Already we have seen there are two types of convections, natural and forced. The natural convection occurs when the temperature gradient in the system generate localized density differences, which result in flow of currents. Means whenever we are going to heat some of the things, the movement of that particular fluid takes place from the lower level to the higher level. But in forced convection, flow of currents are set in motion by an external agent such as stirrer or pump, that already I have told you. Heat transfer per unit surface through convection was first described by Isaac Newton, and the relation of it is known as Newton's law of cooling. Now, what this Newton's law of cooling states? It states that whatever the flow of heat transfer, or heat transferred per unit time, is directly proportional to all these things, whatever the temperature difference between the surface and the bulk fluid which is available one, and the area of transfer of heat, and whatever the proportionality constant which is coming is nothing but the convective heat transfer coefficient. Okay, so Q is directly proportional to the area through which the heat transfer takes place, as well as the temperature difference or temperature gradient between the surface and the whatever the fluid, that may be gas, that may be liquid, which is nearer to it. That is Q is equal to H in delta T. The convective heat transfer coefficient H is dependent on through which medium which is used, whether gas or liquid. Then the flow properties such as velocity, viscosity, and other flow and temperature dependent properties are there. So we will solve certain numericals on the basis of this particular Newton's law of cooling. Heat transfer coefficient has SI units in watts per meter square Kelvin. and it is the inverse of thermal insulation. That is the property which is used for insulating materials. A third mode of heat transfer is the radiation. Now, the radiation, as far as energy, is generally radiated from all the materials in the form of electromagnetic waves or electromagnetic radiations, you can say. Any kind of material is capable of doing all these things. So radiation is also described as the flow of heat from one place to another place by means of electromagnetic waves. All bodies are responsible for either absorbing or either emitting such a kind of radiations. Now, no medium is required between two bodies for heat transfer to take place. No medium is required between two bodies for heat transfer to take place as far as the radiation is considered. One heat transfer through vacuum is called as thermal radiation. Now, the law which governs this law radiation is nothing but the Stephen Boltzmann's law, which gives us the radioactive heat transfer as per this particular law, which is that according to this law, the flow of heat is directly proportional to the area as far as emitting that particular radiation of the body, and the fourth power of the absolute temperature. Uh, and whatever the proportionality constant is known as the Stephen Boltzmann's constant sigma. So Q is the heat transfer per unit time. Sigma is the Stephen Boltzmann's constant. A is the area of emitting body, and T is the absolute temperature. So an electric bulb in a room produces both light and radiant heat. You might have observed this kind of situation that if an electric bulb is of 60 watt, 100 watt, maybe 150 watt, then as per its wattage goes on increasing, it gives the light in proper manner, but as well as along with that, the heat content of that particular room, wherever it is just placed, one is increased, one that is due to the radiation. The radiant heat is absorbed by the materials in the room, which is in turn give out the radiant heat of lower energy, and which increases the temperature of that particular room. So because of this nature of production, radiant heat is an electromagnetic wave that causes heating effect in objects, that absorbs it. So that is the thing. Bulb which radiates, it will be absorbed by the materials inside the room, and it will re-radiate again, so that the increase in temperature can take place. Heat exchanger is the last part. We will not go into the details of this one. Heat exchanger is nothing but it is required to maintain the bioprocesses at constant temperatures. The various applications are in case of milk industries, in case of food processing industries, in case of boiler is nothing but one kind of heat exchanger. So for doing all these things, for getting the phase changes in various, you can say, liquids, various types of gases, you can have the heat exchangers. This biological fermentation is a major source of heat, and therefore, in most cases, bioreactors need cooling. In case of heat exchangers, there is exchange of heat. In case of bioprocesses, it's always between fluids, and that should not mix with each other. So for that purpose, there should be separation. So fluids are get separated using a highly conducting medium. Such a systems are called as heat exchangers. There is no direct contact. Whenever the exchange of heat or exchange of any kind of heat energy will take place from one fluid to another fluid, that may be gas and liquid, that may be liquid and liquid, or that may be any kind of medium to another kind of medium. Various designs of heat reactors used for heat exchange in bioreactors may include, now don't consider bioreactor, this is the one example here it has taken: an external jacket or coil through which steam or cooling water is circulated, internal located helical or baffle coils, or maybe external heat exchangers. These are the things. These are some of the figures which are showing you that what do you mean by the heat exchangers. That means if suppose the one of the heating or cooling in medium means through this particular tube certain hot fluid is present, or a here cool fluid is in, and inside this one whatever the that may be gas or that may be any kind of another fluid which is present at high temperature. So this cool fluid which is passing through this particular pipes will be coming here and becoming again hot. Here in this case it becomes hot, here it is at cool condition, okay, and inside this one again there is a hot, you can say, any kind of another fluid. So whenever it is passing through this particular inside this container, these tubes, and the fluid is passing which is cold, it gets extract heat from that particular source which is available when it becomes hot, and then it is given to the required destination purpose. So in this way, the heat exchangers can work, but we will not go into details, because what do you mean by heat exchanger? It is nothing but a system which is used for what purpose? So that there is a transfer of heat from one source, major source of heat, to the another, you can say the sub source, you can say systems, or you can say sub another material, that may be liquid, or that may be gas, so that its properties, its, you can say, temperature can be changed. It may be lower, it may be enhanced, and it will be is provided to the destination purpose. So this is all about the in short explanation of heat exchangers. So this is from my side. These are the references from which I have taken all this stuff. So thank you very much.